So Professor Min give us a great talk on the advanced models in 3D deep learning. Next, I will focus on and discuss a few representative studies and deep learning algorithms on 3D data learning. We live in a 3D world. All the objects and environment around us are in 3D, and without the ability to understand the 3D environment, we won't be able to achieve any intelligence. And for machine, it's kind of the same. So today, many applications are powered by 3D that include the robotics, where the robot needs to perceive the environment, and autonomous driving, where the 3D sensors on the car need to detect the pedestrians and the cars on the street, and the augmented reality and virtual reality applications, where the environment is perceived by the sensor and presented to the reviewer, and the 3D medical image processing, such as the CT and MRI images. Those images are 3D, and we need 3D data processing to analyze those kind of data. So all these applications has one thing in common. That is, we need to understand the environment or patterns in the 3D input data. Here, when we deploy a 3D sensor, for example, a LiDAR, a depth camera or stereo vision camera to measure the distance to the obstacles around us, the representations of the 3D environment is usually given as a set of points, which we refer to as cloud point and point cloud, where each point is parameterized by the XYZ coordinates in the 3D space. And by understanding the point cloud, we mean that we want to recognize what are these things and which part belongs to which. This is sometimes called a segmentation, and which part belongs to, we can see this part belongs to the desk or this part belongs to the person. So we refer to these type of learning tasks as classification task and segmentation task. Of course, there are other type of applications such as the object detection and tracking, as Professor Mia was talking about. So the question is really, how we can do deep learning on 3D? So traditionally, the traditional methods which have been developed for decades are physics-based. In primary, these methods refer to the multi-view geometry. Suppose you have an object there, like the cubic on the top, you can put cameras around it and have pictures from multiple views. Now you are able to find correspondence across the views and solve certain light transport problem to estimate the 3D geometry. So the key point here is to solve the image formation problem using mathematical tools. It is basically solving mathematical equations. On the other hand, the learning-based approach has a different starting point. Learning is knowledge-based. So the learning-based approach, it represents how we human look at things. So when we human look at, for example, this chalk drawing in the street, we see a 2D images, but in our mind, our brain perceive it in 3D space through hallucinations. This happens because we have the knowledge of 3D, and there are certain prior knowledge encoded from our past experience. So what we want is to capture this prior knowledge with learning and apply the learned data prior knowledge to new data so that the machine is able to understand the 2D data. Before we're talking about deep learning algorithm, let's have a look at at the 3D data representations. So we know that deep learning achieved great success in processing audio and image inputs. And these data are usually represented in a regular or rasterized format, basically a 1D or 2D arrays. However, for 3D data, there are certain structures that make them not regular. For example, the point cloud, graph, and mesh. Those are the basic representations in 3D. So the representation of a 3D data input actually is itself a great challenge for deep learning. And I should mention that different representations are often used in different applications. So the deep learning algorithm also need to be tailored for each application. So among these representations, point cloud is the basic form of 3D data given by many sensors, such as the LiDAR sensor. And the point cloud is a set of coordinates, so X, Y, Z coordinates. So you have the set of points, and also the and mesh is another basic form. And you have the set of points, and you also have the relations between the points. So if we consider the entity as points and relationship as edges, this can also be represented as a graph. Okay, so today we will mainly focus on the classification task. So we have the input data, and we want to assign certain semantic labels to it. So here we have input a car, and we want to output, okay, this is a car. Now, I want to share with you some popular deep learning models defined for different kinds of 3D representations that include the multi-view CNN, the volumetric CNN, which include the Voxel CNN and Octree CNN. And the last category is the point networks, which directly learn from the point cloud without voxelization. Among the point network, I will mainly focus on the PointNet model. And there are many others work based on spectral convolution, spherical convolution, and also graph neural networks. Okay. So the first is the multi-view convolutional neural network. So you have a 3D object here. You can place a number of cameras around it and then project it into different viewpoints. That gives you a number of RGB and depth maps. So a straightforward way to do deep learning is just for each viewpoint, we can process it independently and then aggregate the features we have extract from each viewpoint together. So this is called a view pooling that gives us the feature of the 3D object. Then we can apply an additional stage for classification or segmentation. Here in the picture, this is the architecture of the multi-view CNN. The idea is quite straightforward. It actually achieved good performance around, around 90% classification accuracy, which is a lot better than the traditional mathematical based approach, the first two. So these type of methods are able to leverage the existing image classification methods. And the other advantage is that they can use pre-trained models on ImageNet and other 2D neural networks, which is already very popular, well established in the field, and to extract or train features. But the disadvantage is that we need to do certain projection, right? So that's why we can see papers discussing how to select the best camera positions, how to select how to optimize the projections. In addition, it's hard to handle noisy inputs or incomplete data. And also it's hard to provide translation or rotation invariance. But rotation and translation invariance is very important because when we rotate the input object, we don't want the model to fail to recognize the objects. Okay, so now the question is that can we do deep learning natively in the 3D space without 2D, 3D projection? And the answer is yes. And volumetric CNN is this type of research. The idea is now, given 3D data, we first try to build a certain voxelized presentation. So we will decompose this space into cells, where each cell is basically a small cuboid. And then we will record certain information in the cuboid. For example, we could record a binary or indicator variables indicating whether this cuboid, or whether this cell is occupied or not by the object surface. And this process is called voxelization. It's a process of converting the data to, sorry, it's a process of converting a data structure into a vectorized image. Then after voxelization, it's very straightforward to extend the existing 2D convolution to 3D. So here I want to show you an low-level idea of 3D convolution. So in the traditional 2D convolution, we have our 3D kernel moves into in two directions, the x and y. And the three dimensions are the width, height, and depth. The depth is usually 3 for RGB images. So similarly, we can define our 3D convolution, we can define the 4D convolution kernel for our 3D convolution. So we just need to design the 4D kernel and move it in 3D dimensions, X, Y, and Z. Okay, so a representative algorithm in this line of research is the 3D ShapeNets. The input of the 3D ShapeNets are voxelized images, and the input resolution is 30 by 30 by 30, so which is 27,000 cuboids. So you can see the major problem of voxelized CNN, that is the computational complexity. So as the input resolution increases, the complexity grows cubically. So the challenge is that when we have, we will have very high complexity in terms of computation and storage, which are cubic with respect to the input resolution. So many papers use lower resolutions, such as 30 by 30 by 30, discrete voxels to have a reasonable computational complexity. But the problem is that this introduces information loss and huge information loss, and which we don't want. Okay, so now the question is that, is it possible to reduce the complexity while still have the power? There are many works to address this issue, and one direction is to use the Octree. The idea is based on the observation that with increasing input resolution, the grid occupation ratio decreases. So as we discretize the space finer and finer, the occupancy on the surface is getting more sparse. So we could address this issue by using a special data structure called the Octree. So here in the image, I'm showing an Octree. So Octree is a hierarchical data structure to represent the sparse voxel representation. The basic idea is to partition a space into smaller spaces. So each cubic is partitioned into 8 smaller cubics. And if the cubic has some certain information. For example, the surface is, it has a surface intersected in that cubic. You further partition it into another 8 smaller cubics. Otherwise, you don't do it. So this gives us a hierarchical tree structure to store our data. So to do convolution, we need to know the neighboring cells of each cell. So we need to index those Octree. So in practice, we can use hash tables to do that. The OCNN is this type of convolutional neural network, and using the Octree representation. It's able to scale the resolution of the input to 256 by 256 by 256, which is a lot finer than the dense representations. But the limitation is that these type of neural network usually need careful engineering. The optimization could be difficult, and it is not flexible. And the one limitation is that it still needs voxelization. But we know that the raw 3D data we get from the sensor, such as the LiDAR sensor, are the most straightforward representation is the 3D point cloud. So we don't want voxelization. Then the question is that, can we directly learn from the point cloud, from the coordinates without any conversion to images or without any voxelization process? So now I'm going to introduce the PointNet, which is proposed by Chi from Stanford. The PointNet is a representative model and the first model in this line of research. It is an end-to-end learning model for point set processing. The core challenge it addresses is how to handle the unordered point set input. So what does that mean? So if we, when we store the point cloud in our storage, for example, in the GPU memory, assume it has a 2D array where each row represents a point and each column corresponds to the dimensions, in this case, X, Y, Z coordinates. Now, if we change the order of the inputs, when the neural network processes it, it shouldn't give different outputs. So different orders should have the same results. This is called permutation invariance. Suppose there are endpoints in the set, then the model should be invariant to n factorial permutations. The authors of the PointNet, they demonstrate that we can use symmetric functions to achieve permutation invariance. For example, the max function, the result doesn't change no matter how you order the input points. But the problem is that how to do this by neural network. So the author, they propose a way to construct the symmetric approximation function by neural networks. The basic idea is that for each point in the set, they use a small neural network, multi-layer perception, to process it, and independently and identically. This gives a high dimensional embedding of the node, of the point. And then they use a simple symmetric function here, a max polling function, to combine the encodings of points together. This gives a single high dimension vector of the global shape of the input. Then we can apply a second neural network here, another multi-layer perception, for example, to output prediction scores. Yeah, kind of block the image. So here, the first image shows the architecture of the PointNet. The input is n by 3 points, endpoints. Each point has 3 coordinates, and the first layer is a transformation layer. The idea is to map the input through a neural network. And in the end, we get 3x3 transformation, we get a 3x3 matrix. This is the transform. And we multiplied the n/3 input with the 3x3 transformation matrix. In the end, we get n/3 points. So this part is to align the inputs with a transformer network. And the purpose is to provide translation or rotation invariance. Then we have the endpoints again. We can apply the basic construct of PointNet and use NLP to MLP to map the input to 64 encodings. So we have n/64 representations. And then we apply the transformer network again for embedding space alignment, again for the rotation invariance, and then apply MLP for each node again, which gives us n/124 representations. Finally, we apply a symmetric function here, the max Pauling function, to aggregate, to combine all the embeddings of each point together as a global representation. So until here, we have got the global representation of the 3D input. Finally, we can have another NLP to associate a feature with the output. This is a simple architecture, not computationally intensive, but achieves very good results. Here we can see it achieves around 89.2 with only one single view, which is equivalent to the multi-view CNN, which has 80 different views. Yeah, similar classification results. Here this image visualizes the what have been learned by the PointNet. So we can see it learns the outline structure of the shape as critical point sets. And of course, it has some limitations itself. For example, the local pattern for each point are not captured. This is because the PointNet structure, they extract a representation for each node, then aggregate it into a global representation. So it really didn't capture any local or neighboring information about the point. And also the global feature depends on the absolute coordinates, and it's hard to generalize to complex things. So what they did is that they later on they proposed a PointNet++, and this is a hierarchical network that applies PointNet recursively on a nested partitioning of the input point cloud. So it sort of solved the problem of that neighboring local information problem. And thank you. That'll be the end of my talk. So I hope you enjoyed. Thank you.
Yeah, thanks, Min. Yeah, very good timing, and lots of the advanced method you have introduced. Yeah, thanks a lot. Maybe we have one question. We are about time to move on. Let me see if there are any online questions. Or people from floor? Yeah. Yeah, sure.
Just a quick one. Will it take a long time for calculation? Seems you have a lot of dots there. Just curious.
Yeah, some of the methods depend on the input resolution. So for example, the volumetric CNN, which requires to convert the input cloud point clouds to voxels. So depending on how many voxels there are, the depending on the methodologies, for example, the voxelization CNN, it's increased like cubically with the increase of the input resolution. But there are other methods Professor Min was talking about that is able to address this problem. So one simple way I learned is the Octree. So Octree is like an indexed. So you don't care about, so with a voxel, so you don't care about the, you only care about the voxels on the surface of the objects. You don't care about the others, right? So you can have an index Octree structure to index the voxels you care about. So in this way, it kind of reduce the computation to some extent. Yeah, but there are other methods.
Yeah, thanks, Lily's question. Yeah, I think Kangjin is online. Would you like to ask the question yourself?
Yeah.
Yes, please go ahead.
Hello? Can you hear me? Hello? Hello?
Hello, yeah, we can hear you, but we can't hear the whole sentence.
Okay, so I was just trying to ask, what's the difference between a rasterized volume and a point cloud? It's
Yeah, I think the question he typed here is that what's the difference between a raster-sized volume and a point cloud? Raster-sized,
yeah,
point cloud.
So there is a difference. So the point cloud is a irregular data structure. So it's not rasterized. And if we want to, the rasterized version of it, we need to convert it into voxel representation. For example, in the voxel CNN, the input is voxelized images that is rasterized. Yeah, but 3D, like 3D input data, they have different representations. One category is the rectorized input. These categories will include multi-view images, multi-view RGB depth images, and the voxelized images. And the other direction is the not regular data structure, and this includes the point cloud, the graph, and the mesh.
Great. Yeah. Thanks again, Maggie. Yeah, thanks online people and also Kanji's question. Yeah, probably, yeah, again, we can continue the discussion later. Yeah, all the best to Min's special group, the early career special group in AI. Yeah. Now, yeah, these are the two main talks. And then next, we like to share what the kind of projects we are running, within our imaging sensing group. And before that, I think the deputy head of research, Professor O'Brien, to give some overall, introduction of the research we are doing, especially the imaging and sensing area.